Hi, everyone. It's nice to have you all here. And today what I'd like to talk to you about is data modeling. So we will be talking about initially probability distributions, random variables, and then we'll move on to sort of how to draw random variables from probability distributions, and so forth. So a large portion of this class is sort of focused on starting from data, and from data deducing causes, or in other words, learning models. This is very much unlike sort of traditional modeling, whether it be in physical, chemistry, or other areas of the natural sciences, where oftentimes you start with models and you try to make predictions. And then you would compare your predictions to the data itself. In this case here, actually, we'll be going in the opposite direction. We start from the data and try to learn the modeling. And these types of approaches are sometimes called inverse modeling. So, a large part of this course is based on various inverse modeling techniques for problems of the natural sciences. So let's go ahead and clear this. And the book that I will be using is this book right here. It's the book that I've specifically written for this course. It's called Data Modeling for the Sciences. And oftentimes when we do data modeling, we talk about probabilities. And we can ask ourselves the question, why probabilities? What's special? Why do we deal with random variables and probabilities and so forth? So why work with probabilities? And the answer actually is quite simple. Even if we're working with systems that are kind of deterministic, the idea is that we always carry out measurements, and measurements always have noise. So fundamentally, we find ourselves always dealing with probabilities and random variables and noisy output. And from that noisy output, again, trying to deduce causes. So why work with probabilities? Well, this is because measurements oftentimes have noise. So, an important concept here is the concept of the random variable. And we're going to refer to a random variable using the following symbol. Typically, it's going to be referred to as big W. The random variable itself is sort of an abstract concept. And when we carry out a measurement, that random variable, big W, is assigned a value. And that value we call small w. So for example, the big W could be a random variable telling us about a potential outcome for a coin flip. The small w would specifically be the heads or the tails. Now, whenever we talk about measurements, we oftentimes have very many of them. So we use kind of this convenient notation indicating a vector or an array over all of the different w's. So whenever I indicate this w1 to n, or it could be the realized values, which would, in the case of a coin flip, be heads or tails, refer to them in the following fashion. So oftentimes I won't be writing the entire array as it is written here, and simply use this notation right here. So we're going to go ahead and clear all at this point. So we've talked about sort of learning models. So one potential way to move forward is to say, for example, suppose that my model is a bell curve. Another name for a bell curve is a Gaussian distribution. Or also called a normal distribution. Now, when we deal with Gaussians, in case we're familiar with them, there are generally two parameters that we care to learn. One of them is the mean of the variance, the mean of the Gaussian, usually referred to as mu, and another one is the standard deviation. So here mu is the mean, and sigma is the standard deviation. Oftentimes we will talk about the variance, which is mu squared. So suppose that I were to draw some random points. So these will be my W's that I'm drawing from a Gaussian distribution. So I should say these will be my W's, and this will be my index n. So my first data point, for example, may be here. When I draw a second data point, it may be here. A third data point might be there. A fourth data point might be here, and so on and so forth. So my data might look something like this. Now, if I were to histogram this data, ideally the data itself will be centered around the mean with some spread related to the standard deviation. So here's an example of data modeling. It's to start off with the W, 1 to n, realizations of my Gaussian, of drawing samples from my Gaussian distribution, and to learn from those draws my mean and the variance, and the variance of the distribution. Gaussians are specific or a special family of distributions. They have two parameters, so they're called two-parameter distributions. Sometimes the way we write the Gaussian is as follows. We will say that the random variable, big W, is drawn from a normal distribution. Remember, that's another name for a Gaussian, with two parameters, mu and nu. Not all distributions have two parameters. Some, which we'll look at very shortly, have one, and others, for example, have very many. So one compact way of saying things is that from the W, 1 to n, we'd like to be able to learn, for example, parameters of a distribution 1 to k. Now, for the specific case of the Gaussian, or the normal distribution equivalently, we would go from W, 1 to n, collect n data points, and learn two parameters. And those two parameters will be the mean and the variance, or equivalently the mean and the standard deviation. So, when we talk about probability distributions, and you've seen me do this in the last slide, we often use the following notation. We will say that some random variable, R, is being drawn from some probability distribution, which we refer to as P. Why am I calling it R? Typically, I reserve W for data. That's a specific type of random variable. And R is going to be a more general type of random variable. So this statement here should read as the random variable big R, and by the way, oftentimes I'll be referring to random variable as RV to make this simple, but the random variable big R is drawn from some distribution P. Now, for the example of the Gaussian, we would say that R is drawn from a normal distribution, or may be drawn from a normal distribution, with some mean mu and some variance nu. Now, R is sort of the unrealized random variable. It's in its abstract notation. The normal here is a distribution. Oftentimes, we evaluate or we consider probability densities, and let's write that down. Which we write out as P of R. For each probability distribution, or oftentimes, for each probability distribution there exists a probability density. Now, the form for the probability density for the normal takes on the following form. I'm going to rewrite P of R as 1 over square root 2 pi nu. We'll explain where this comes from in a second, or shortly I should say, times the exponential of negative 1/2 r minus mu squared divided by sigma squared, or simply nu. This is the form for the probability density coinciding with the normal distribution. It has two parameters, mu and nu. Nu here also appears in the prefactor. And this probability density has the r in it. The r being the point at which this P of R is being evaluated. So sometimes, if I'm working with a probability density, I might write r semicolon mu and nu, while if I'm talking about the general probability distribution, not yet evaluated at a point, I may use the following notation. So this would be for the probability density, and this here would be for the probability distribution. Now, whenever I write down that a random variable is drawn from a distribution, as I write this encodes certain information already sort of pre-assumed. So let me go ahead and say that R is drawn from a normal distribution with mean mu and variance nu. Okay, so what is encoded in this line here? For example, what's encoded is that allowed values of R can be realized to R over the domain ranging from minus infinity to positive infinity. So in writing something like this down, as I've written it here, what it implies essentially is the domain over which my random variable can be realized. What else is encoded in this statement? Well, something interesting. The mean of R itself is evaluated as the integral minus infinity to infinity dr P of R times R. Similarly, the variance of R is written as minus infinity to infinity dr P of R R minus mu squared. The standard deviation then is the square root of this quantity here. There's another piece of information that's also encoded in writing this equation down here. Just going to clear this. And that piece of information that's encoded is the fact that the distribution, or the probability of finding some R between some R min and some R max is computed as follows. So the probability is equal to the integral R min to R max dr P of R. Now right off the bat, if P of R is a normal distribution, or equivalently also called a Gaussian, is a normal, then this integral here doesn't take such a simple form. In fact, it takes, or it can be expressed as an error function. The error function definition typically is written as 2 over square root pi 0 to r dr prime e to the minus 1/2 r prime squared. Right? So through an appropriate rescaling of these variables here, I can express this probability using error functions. So, the Gaussian we've talked about, or the normal distribution we've talked about, because it pops up almost everywhere in the natural sciences, for fundamental reasons that pertain to things like the central limit theorem, and other things that we may touch upon later in class. But there's another distribution that often pops up very often, and this one we'll encounter in Chapter 2, and that's the exponential distribution. So we've talked about the normal. Now let's talk about the exponential. And the exponential distribution is a little bit simpler because it's a one-parameter family. So it only has one parameter. This parameter oftentimes is called a scale, and it's referred to as lambda. Sometimes people refer to lambda as a rate as well, because oftentimes the exponential distribution pops up in dynamical problems. But let's go ahead and talk about the exponential for just a second. So we would say that some random variable r is drawn from an exponential distribution with one parameter, and we call that parameter lambda. So writing something like this encodes what information? Well, it encodes the fact that the domain of R includes the region from 0 to positive infinity. So there are no negative draws from an exponential distribution. It also encodes sort of the form for the exponential distribution, which is lambda e to the minus lambda r. And finally, it encodes information about the mean of r, which is computed as 0 to infinity dr r p of r, which if I do this exponential integral will give me 1 over lambda. And finally, of course, the probability is obtained over some range dr prime p of r prime. Now there's just a few things I think that are worth mentioning. We know that whatever lies in an exponential has to be unitless. So if r has units of time, then lambda must have units of inverse time. Similarly, if r has units of meters, then lambda has to have units of inverse meters. So we notice from this that the mean of r correctly is a quantity that has units of 1 over lambda, because we know that r has the same units as 1 over lambda. Something else that's interesting about units, something basic but still worth pointing out, is the fact that if r has units of 1 over lambda, then p of r, the density, better have units of 1 over r. Right? So this, therefore, better be unitless in order for r to have the same units as 1 over lambda, since lambda times r is unitless. So let's go ahead and clear this and just make one little note on units. R and P of R have inverse units. So if R is second, then P of R is second to the minus 1, sometimes also called a hertz. Now there's something else also worth mentioning, which is the concept of normalization. So what do I mean by that? Well, what is the probability for an exponential, for example, that the random variable be anywhere from 0 to infinity? That probability better be equal to 1, right? So the probability that the random variable be realized to anything should be equal to 1. Well, interesting. 1, of course, is unitless, so this is another way of verifying that R and P of R better have different units, because if R is seconds and P of R is inverse seconds, then this quantity here is, as expected, unitless. So we can ask ourselves the question, where did the lambda come from here? Well, it came from the condition that P of R dr integrated from 0 to infinity must be equal to 1. In other words, it came from the normalization condition. The condition that P of R, when integrated over all of its domain, must be equal to 1 is called a normalization condition. Similarly, for the Gaussian, it would be a similar thing, except in this case, the domain of the Gaussian extends from minus infinity to infinity, d of r, p of r, and then we would find that this is equal to 1. And that's ultimately what sets that prefactor of 1 over 2 pi times the variance that we had seen earlier for the Gaussian. Now, there's perhaps one last distribution that I'd like to introduce. There's going to be many throughout the class, but maybe one last one of interest, and it's or immediate interest, and that's the multivariate Gaussian. Why am I talking about the multivariate Gaussian? There's plenty of single variable distributions that we can keep talking about. For example, the Poisson distribution, the gamma distribution, all kinds of other distributions that we'll be mentioning. Is because this is an example of a distribution that depends, or whose probability density equivalently depends on very many variables. For example, it can depend on n variables. So, for example, if we look at P of R versus R for a normal distribution with some mean mu and some standard deviation sigma, that's in one dimension. But what if I want to sort of look at hills and valleys? So what I'm going to do now is to plot sort of a topographical map. Here this will be the mu. And maybe my Gaussian, if I were to look at it from the top, which is here, sort of spreads out in 2 dimensions, R1, R2. And if it's 2 dimensions, then why not 3, 4, 5, 6, and so forth? So this is an example not of a simple normal distribution, but of a bivariate normal distribution. It depends on 2 different parameters, R1 and R2. It has a mean that depends on 2 quantities, mu1 and mu2, right? And it also has a variance in this direction, in that direction, and these 2 variables, and it's not a completely symmetric Gaussian. We notice that it seems to be sort of skewed along the diagonal direction. So there's one way of sort of expressing this, which I'll write down immediately at this point. So for the bivariate, or more generally the multivariate, normal, I would write P of R 1 over square root 2 pi raised to the m if I have an m-dimensional Gaussian multiplied by the determinant of v. I'll explain what v is in a second. Multiplied by the exponential of negative 1/2 r minus mu transpose multiplied by v inverse r minus mu. Let's put the transpose by convention here. So my r and my mu here are vectors or arrays, and for an m-dimensional multivariate Gaussian, they're going to be arrays of dimension m. My v is called a covariance matrix. And the dimensions of the matrix are m by m. If a matrix is completely, or if I should say distribution is completely symmetric, then typically the off diagonals of V are 0. But if we notice some kind of skewness, or some kind of tilt, I should say more accurately, then more generally the V can have off diagonal elements. We'll be exploring a lot more of that as we start discussing Gaussian processes. And I think this is a good place to end the first tidbit on random variables and distributions. Thank you.